talks will get into a different scientific mood. So in 2000, so Pauchy organized a community in Taiwan tried some efforts in cosmology study. So they owned this program, academic excellence from the Ministry of Education, and then organized many initiatives in cosmology, astrophysics work. In fact, a week ago, there was a memorial session also at one of the COSPA meeting in Yangzhou. That the meeting series allows an international series taken over all around the world, mostly Asian and Pacific countries. So that conference was initiated from here due to this cosmology sort of program with the Ministry of Education. So during that time, then he had a lot of collaborations with the academic syndicat. So next talk was given by Pauchy. He was one of the leader of the program. So let's welcome Professor Pauchy.
Well, it's my sad duty to come and report on what we've been doing. My first memory of Pauchy is also from the very early days, and also this booming, deep voice. I think at a Chinese physicist meeting in the States. Of course, I was just a young person then, and was just very impressed by this powerful presence he had, even in those early days. The next time I really got to know him was after I came back to replace Woei-Yann at IAA. And I would say at that time, things were a bit turbulent between the Academia Sinica and Taiwan. It's not, I think it's sort of a historical conflict between the academy and university, because the academy is true, had a lot of research resources, and the university had the students. So how to work together was quite difficult. My charge from Yuan Li at the time, I said, what is my charge when I come to Taiwan? He says, your job is to move to Taiwan, move to Taiwan to improve the relation between Academia Sinica and NTU. And my window, the person who helped me was in fact Pauchy. Right? He was my window. And when I knew him, did not know him as a research scientist, but as an administrator, right? The vision that he was projecting was how we were supposed to build the astrophysics in Taiwan together. He had in mind specifically to move the academy to Taiwan, and he had proposed, together with this COSPA program. So my job was to implement their vision, and I've been doing that ever since. And I hope that, I think he does, from our discussions later, that he agrees that we did a good job, okay? So Pauchy's imprints on Taiwan astrophysics is quite deep, So from Taiwan side, of course, you are thinking about the physics side. But from the astronomy side, his imprints, in my mind, are quite deep. Not only from the IAA point of view, which I will tell you about, but also at the other universities, okay? So today, where IAA is in Taiwan, right? Where we are physically and scientifically began with the vision that he had in those days, okay? How to do it. And COSPA pushed the development. His idea at the time was not just between between Taida and the academy, but also the other university in Taiwan. So we had this program that's quite integrated with an initiative of every place, trying to grow the effort in every place. And across the board, it wasn't just cosmology, but it was strengthening all the research areas. So this definitely strengthened our collaboration between the two units. I think it could have been even stronger. I think there's room to even push it more. I'll tell you about that later. So most importantly, this COSPA program that established the observational cosmology program in Taiwan. We built the Amoeba, which is this microwave background instrument, but that was not the main product. The main product from the Amoeba project led to these other projects that I'll tell you about, ALMA, GLT, but also within COSPA, we began to engage the Large Optical Telescope, the Canada-France-Hawaii telescope, and that led to Subaru, and today we're working on the extremely large telescope in Europe. We're looking at collaborating with them. But the main product were the young people through these programs so many years ago who are now leading the efforts in Taiwan. And through this effort also we engage industry very strongly, and that collaboration with industry remains very vibrant today. They are our backbone, which allows the astronomy efforts in Taiwan to push ahead. So first I show you what he had done for us infrastructure-wise, right? He made this building appear, right? He got Yuan Li to agree with Taida to raise the budget to build this astromath building down the road. Up there, he's at the opening ceremony, and he gave the speech at our opening ceremony. And then later on the top floor, on the 10th floor, we have a garden, which was in fact dedicated to our mutual friend Yuan Qi. And there's Pauchy together with Sheng Yi was there, and Kali Wu was there that day together with Qi's wife. We're dedicating that garden for him. So I have some idea what we should do for Pauchy also. And this second one is when we completed Amoeba. This was in 2006. Amoeba made possible because of Pauchy's campaigning on behalf of the COSPA program all those years. It was built on Mauna Loa in Hawaii. That's the picture on the left there. It's an interferometer with 13 elements to map the cosmic microwave background. And there he is, Pauchy, with the important people in the picture. As you can see, Yuan Li and Wong Chi-wei. Wong Chi-wei was just becoming Academy President around that time, and then President of Taida, of course. And down below, Fred and Pauchy are there, and Jane and Pauchy was giving a speech, dedication of that instrument. And that's Frank Shu over there in the middle, presenting Pauchy with a picture of the telescope. So in IAA, we have this instrument program, which we have produced back starting from 2003. The yellow numbers are the delivery dates of these projects. So you can see the COSPA program began, somewhere around 2002. And you can see at that point, very little was in the IAA. Practically nothing. We're just working on the submillimeter array, putting together this interferometer on Mauna Kea. But from that COSPA program, which launched the Amoeba, that program led to us to join ALMA. Why is that? Because we had the young people and the receiver lab development and the instrument scientists that were trained through the Amoeba program. And by that I mean not only the people who built receivers, but the electronics, the collaboration with Taida's WE department was very important for building devices, and that allowed us to participate in ALMA to deliver a number of important instruments for that program. And that afterwards led to the Greenland telescope, which we're deploying right now onto Greenland. And the other path below, we already started on Taos 1 at that time. This was the occultation experiment for the Kuiper belt objects that was on top of Lulin. But we knew that optical astronomy must grow also. So at that point, CFHT became part of the optical program. And participating in the wide-field infrared camera, which was a core part of that COSPA program, installed later on led to other projects at CFHT, but then led to this building program participation in Subaru, which are very important. And why are these things important? It's because all of those projects that we built, in fact, are driven towards the cosmology. Okay? For example, amoeba, here you see on top of Mauna Loa, produces these images of clusters. These are the Sunyaev-Sadovich effect of a cluster where the electrons in the cluster interacts, scattering the microwave background, right? And that scattering basically changes the energy profile, and therefore you will see the slight cooling towards the cluster, depending on the wavelength. Sometimes it's heating, okay, if you're at high frequency. But that cooling signature is very important. The reason for that is that this signature, which is acting on the microwave background, is independent of redshift. Okay? So it's a probe of matter very far away. When the optical signatures goes away, we can continue to see the signature. Okay? So more importantly, this program actually led to development of lots of equipment, highlighting in the top, of course, the MIMIC device development, which is with Woei-Yann in the WE department. But also within our own department, with our Union Institute, we began to develop this very fast A to D converters, analog digital devices. This converter has a very high speed of 5 gigasample per second. Now the device is at 10 gigasample per second, and these devices are now actually implemented in many observatories. So it's one of the key products from this amoeba project, right? It produces equipment starting from amoeba, but it branches out to many other things. So this is just to show that, you know, in our phase of development from the 7-element small telescope to the larger 1.2 meter on the 13 elements, you can see the images sharpens, and then it actually correlates with the weak lensing results from Subaru later on that we work on. And these things are very important because, you know, it's a tracer. I don't have time to explain everything here, but the lensing, the gravitational lensing, which produced the dark matter, instead correlated with the X-rays, correlated with optical, it's correlated with SZ effects, and it allows us to probe the distant universe. This is the target of this kind of science. Then we moved on and built the ALMA project. This has been operating since 2013, and this project has the footprint, has the fingerprints of Pauchy again, because you see all of these developments, such as the front-end systems, which we integrated in Taiwan, the sub-reflector system, which we produced in Taiwan, the testing lines, the receiver transfer vehicles, these were all produced in Taiwan. These were made possible because of this collaboration with the industry that we began, starting with amoeba and starting with the training of these people, which allow us to, in fact, when we executed these experiments for ALMA, we recover all the funding that were allocated to this project. So this project has zero cash outflow out of Taiwan. That's because of the vision of making astrophysics homegrown, right? This is the point that from COSPA from the very beginning, okay? And of course, what is the influence of this kind of science and cosmology has to do with the fact that the redshift of the radiation from distant universe, and this is a spectral energy distribution of galaxies, M82, as it rolls into the submillimeter band at higher and higher redshift, the radiation gets fainter because it's more distant, but the radiation peak is shifting over. So that combination effect puts most of that light that's shifted over into this particular band in ALMA. Okay, that's very important. That says that no matter how far the galaxy is, because it's rolling in, that peak of the radiation curve continues to become visible, even though the radiation now, the source is further and further away. So this is definitely, we do it. And now, you know, in the submillimeter, we find that there are these galaxies that are predominantly radiating in submillimeter. They are quite special. Why are they special? Because it looks like almost all of them are gravitationally lensed by a foreground object, okay? So how do you know that they are gravitationally lensed? It's because when you see the matter distribution, this is in the ALMA project in different frequency, and you can see the line, the molecular line emission is distributed in this Einstein ring-like pattern, the classic signature of this gravitational lensing. And the distribution of these particular matter is quite important because when you reconstructed the foreground galaxy and cluster, which has gravitational lens the background galaxy, in this case it's a foreground object lensing a much further away galaxy, what they required is a dark matter distribution in the foreground. Okay, so that's the image. The red is the image arc of the molecular gas in the back. In order to accomplish this particular structure, we needed this foreground structure as measured in dark matter. And the interesting thing is the dark matter of this particular dwarf on the side, which says that the dark matter dominate that dwarf. So of course this has some implication for dark matter distribution in the early universe and as the universe evolved. And this is the Greenland telescope that has now been deployed to Greenland. And you can see that it's very close to the north because you can see the North Pole there and the stars trails around that North Pole in this particular telescope. This telescope is one of the products from our ALMA project. It is now deployed to Greenland in 2017. And it, together with JCMG and SMA, which are also projects that we participate in, and ALMA, which we also participate in, forms a gigantic triangle, a telescope the size of the Earth. And this has a maximum baseline of 9,000 kilometers and produces a resolution of 10 microarcsecond. Why is that interesting? It's because it will resolve the shadow of a supermassive black hole and thereby measure for the first time the spin and mass directly for a supermassive black hole. So Taiwan is in this project, including JCMG, SMA, GLT, and ALMA, and this all began starting with that COSPA project so many years ago. So in the end, what you would like to see, the theory would predict what the shadow of the black hole will look like. It will depend whether it's rotating or not. If it is rotating, it will be a little bit squashed. If there's a disk, accretion disk, you might see the bifurcation of the shadow. And of course, the size of the shadow is about 5 times the event horizon, and the shape would then measure the spin. These are the only 2 qualities that you can directly measure from the supermassive black hole, but as we increase the resolution, we should be able to see the GR effects on the edges of the event horizon. So the cosmology, from Taiwan's point of view, we use Amoeba, of course, but then we are also using CFHT and Subaru. So I would like to tell you a little bit more about those particular projects, which are also part of the initiative within COSPA. Okay? The idea is to look at the large-scale structure, measure dark matter, dark energy, and measure the 3-dimensional structure. So the CFHT was the first project that we participated in. We built the wide-field infrared camera, and then these were the early science returns from the CFHT. This is actually looking at gas, cold gas falling onto a galaxy in Perseus, a CD galaxy, which means a giant galaxy in the middle. The gas flow from the cluster, cool gas falling inwards, and we can measure them in different lines. And on the right is actually measuring a very high redshift system, a Z of 7.8 candidate, and that has to do with the fact that we're measuring the spectral energy distribution, so there's something that's visible at the optical wavelength as it goes redder, just the spectrum just disappears. And measuring these spectrum by using these new telescopes with the new filters was one of the main products from the CFHT experiment. But from there, we went on to the Hyper Cam project on the Subaru telescope. So based upon the experience on the Woei-Yann, the person who was involved from the beginning from the CFHT, who is now our chief optical instrumentalist, this is Wang Xianyu at the IAA. He participated in this particular project for the prime cam, and our project was to build the filter exchanger system on this particular very large lens that hangs on the prime focus of the 8.2 meter Subaru telescope, which is the huge telescope for the optical and infrared. And this particular camera, we also delivered other parts such as detectors and so on. But the filter exchanger was actually built in Woei-Yann, and it was a fantastically successful product. So based upon this, we were also participating in the next experiment, which is the prime focus spectrograph. But from this, this particular experiment was actually to map a very large field of view at the time. So it has a field of view almost 1.5 degrees at a time, which is much bigger than the moon. Okay, and from that you can gather a lot of galaxies in your field of view. And what is the effect that you're looking for? You're actually looking for slight distortion of the shape of the galaxies that you observe. Okay, because of lensing, gravitational lensing by dark matter in the field, the shape of the galaxies are slightly distorted, and from that you can work backward and calculate what is the dark matter distribution ought to look like. So this is, for example, one of the first product this year from this hypersuprime cam project, which mapped the structure, as you can see, on 10-degree size scale, and the redshift out to 1. And the redshift is done by these filters in this filter exchanger, which allows us to measure the light toward these systems with a number of points in the filter to measure the spectrum, and from the spectrum we can determine the redshift. Okay? So this can see the structure that you can see forming in the universe out to redshift of 1. This is the other product that we have out of this Subaru telescope. This is again depending on the hypersuprime camera. This is looking for the progenitor of the gravitational wave event, thought to be a binary merger. This binary merger has an error circle that's quite large on the sky from the LIGO experiments. So it is difficult to locate the source of that unless you have a very wide field camera. So this wide field camera map across the sky and in that error circle and discover this particular object, okay, which is seen here in the crosshatch between those dates, August 18th to the 24th, it has faded. Okay. So this particular type of experiments where you can use the wide field to search for the gravitational wave progenitor is actually a very important product coming out of this particular camera. So the next one will be the prime focus spectrometer, and this is also at the prime focus. The idea there is now to have 2400 fiber fed from the prime focus here. So this camera will produce 2400 fiber, which can be repositioned within about a minute. And you can reconfigure the fiber position on the sky in order to focus on 24 objects that you would like to, 2400 objects that you are looking at. So this particular, well, it's no time to discuss this, but it's a very clever device to move the fibers around. So for us, we are building the main prime focus instrument, which is the housing of this. We will take care of all the interface between the structure, take care of the heat exchange, take care of the measurement, metrology camera, and also managing. So a lot of this work comes because we have already done the hypersuprime camera project very successfully, and because of this interaction with our industry, which is Woei-Yann. So this project basically took on many of the tasks that originally was done by JPL. Why did that happen? It was because now Taiwan has this expertise to produce these instruments, and of course we're very cost effective because we're working very closely with the industry. Okay? So in the end, JPL passed the task to us, so we are now a major player on this particular instrument. You can see here the layout a little bit more clearer. 2400 fibers, 1.25 degrees squared, a wavelength about 0.3 to about 1.2 micron, a resolution up to 5,000. Okay? So it's a very sensitive measurement for the spectra. So from the previous figure where you saw the redshift structure, these things will be much, much more accurate because of the fiber, which is then fed the spectrometer in the background, which will then be able to analyze the resolution, analyze the redshift much more accurately because the resolution is 5,000 versus HSC, which is a resolution of about 10, right? So finally, I would like to point out what Pauchy has done for us in addition to all of these things. So of course our building is over here. This is on top of our 10th floor garden. From there, I took a picture yesterday, looking back toward this building, right? So you can see what Pauchy has done. He's built all the tall building on the north side of campus. He has made that happen. And had things gone a little bit better, in fact, the original agreement was that the Academy was going to redevelop these buildings over here also. So my recommendation, I would like to ask Taida to name this particular path, starting from condensed matter to astronomy. That path could be called Pauchy's path, right? This is what he has managed to do for us over time. So I'll stop there.
Thank you all. Some quick questions? Well, if no immediate one, again, we defer to the end.